Hello! If you found this video, chances are your network file is driving you completely crazy. Perhaps you've tried to do a shortest path analysis and had trouble, so you needed to use some kind of a tolerance in your file. Now the problem is that you're zooming in and you can't find these errors. So what I've created is a model that you can use in QGIS and that will permit you to find all of those errors, including things like disconnected nodes. If you're new to network files, I suggest you start by reading this article, Python algorithm for shortest path river network distance calculation considering river flow direction. This is an article that we wrote and that will basically explain to you some of the common problems that we have with network files, and it will also point you to a GitLab site where you can download the algorithm. And this algorithm permitted us to calculate over 360 million shortest path routes in Peru. So if you Google QGIS and plugins, you're probably going to find this page quite quickly. plugins.qgis.org. Now, this page has a new section under Hub, and one is for styles, one is for projects, and one is for models. Now, I've created a model that you can download here, and it's actually three models. The first one is going to check your geometries, the second one is going to check the network file, and the third one is going to fix some of the network files that you're going to be identifying. Now, once you've actually downloaded the files, you can open the processing toolbox and go to the gear icon that we can see here, and you can add the model to the toolbox, click on the files that you want to import, and they will basically appear right here under models. The model is under network analysis, and you will find a different model for every file that you download. Now the first model is going to check the geometries. Here we're basically looking at a linear geometries and we're trying to find errors. So the easiest way is to enter the name of your test network, and you can leave the other fields as they are, unless you're scared of overwriting some information that you already have in your files. Now your original test file is never going to be destroyed or changed unless you do it yourself. So once you've run this tool, you're basically going to have these files here. Now, the first thing is going to be the problem or invalid geometries. These geometries have been dropped, and if you want to know exactly where the errors are in the geometries, you can look at the points file, which is basically the problems, and inside you will find, if you look at the information, you will find the problems that you're having with these geometries. Now these geometries that are here will be dropped in the final file, so unless you fix them, they will be eliminated. You will also see some of the files things that were fixed. So in blue here, we have basically geometries that were multi-part. And in order to do a network analysis, you need to split these into single parts. So all of these lines here have been fixed and are found in the valid geometry. Now, if you're happy with the valid geometry file that you have, you can keep on going to the model 2. Now the first model is check geometries, and basically that was used to make sure that the lines had no errors. The second model is basically going to be checking for network errors. Now these network errors can be things like disconnected lines, overlapping lines, things like this. These are basically errors that are going to give your network some problems. Now, once you start the module, you will need to select the output valid geometries from model 1. You can keep the other variables as they are, and as you can see, there's a whole bunch of output files that are going to be created. The first group of files that are created are the graph files. Now we're going to look at them because it's going to help us understand some of the errors. Now, when you run a network analysis trying to do a shortest path, their computer is, or the algorithm, is basically going to be looking at the graph. Now, the original network is going to be complicated lines, but your graph is basically made of the first point and last point in the line. The lines are called edges in graph theory, and the beginning and the end of a line are graph nodes. Sometimes they're also called vertices. All of these need to be perfectly connected. They all need to be snapped. Here we can also see that we have little arrows. The arrows are basically indicating the direction of the network. It's basically the direction in which the network was vectorized. It is possible to change this by flipping these lines. This is going to be important if you're dealing with rivers, because a river would probably be flowing in this direction and not going towards this direction here. Now, looking at the graph is very interesting because it can show us some of the bigger errors that we are going to be having. Now, over here, we had a whole bunch of multi-line objects that were simplified into multiple single objects or single line objects. If we look at the graph, you can see the nodes. But if we look at the graph edges itself, we can see that all of these nodes are actually disconnected. So this is some of the things that we are going to be fixing while we're running Module 3. The check network model is going to help you create the graph, but it's also going to be flagging 9 potential problems that you might be having with your network. The first is a network direction change. Now, if you had a river and you were dealing with a river current, then every time you have a network direction change, you would have a change in the current. Now, this is a big problem if your changes occur right in the middle of your river. So here we have a situation where we have the beginning of a line going in this direction, which is connected to the beginning of the line going to the other direction. So if you're concerned about the direction that your network was vectorized, then this will flag all of your network direction change problems. One of the biggest problems that you're going to have with the network is finding your disconnected lines. Lines that are basically not snapped. Now, the interesting thing is I've separated the disconnected first nodes from the disconnected end nodes. Now, if this was a river network, these first nodes should not be connected to anything. So these are basically, because basically the current would be flowing in this direction here. There is sometimes, however, especially if you have problems with your network direction, there are situations where you are going to find some first nodes in the middle of your network. And if they are disconnected, if you zoom in, sometimes you will find. Now this error right here is very, very small. It's under 8 millimeters. So it's going to be difficult to find all of these. Now, here we have the end nodes. Now, if your network is vectorized in the right direction, these are going to be the problematic areas. The areas that are in the middle of the graph and that are not connected. So this here is a disconnected end node and basically tells me that this line is has been digitized in this direction here. Now the second model is also going to be checking for a number of other errors. One of the problems is a closed line. Another problem are overlapping lines. we have non-touching lines. So non-touching lines are basically lines that are not connected either by the first node or the last node. Parallel edges are also a problem, especially if you're using a simple graph. In this case here, we have two lines that start here. Basically, we are talking about this line here that starts here and ends here. If you're building a simple graph, the second line is going to disappear and is never going to appear on your graph. That is going to be a problem. You need to use a multigraph in order to use this type of situation. Unfortunately, multigraphs are a lot heavier to deal with. Here we have another problem, and this is only a potential problem. Here we have two lines that are disconnected but crossing. So this line is crossing this line here. Now, if this is an overpass, this is not a problem. But if you need to be, for example, taking the highway and then changing directions, not the highway, but a street, changing direction, then you're definitely going to have a problem because your lines are not connected. So this is also going to help you to find those areas and also to keep those areas if you need to keep them intact. Finally, we are flagging lines that are just too complicated. So we have a good example here where we have a single line that is just too complicated and it is made of a whole bunch of smaller lines. Now these lines could be merged together, but if you do merge the lines, keep in mind that you're going to be modifying the database. Now the problem using the shortest path with a topology tolerance is that sometimes you don't really know what that tolerance should be. So what I've done here is I've created a distance analysis for these disconnected nodes. And basically, if we look here, we have some nodes that have a zero distance. Now these are disconnected because QGIS doesn't seem to be able to put a number here if it's smaller than 10 e to the minus 9. So these are definitely disconnected nodes, but separated by a distance so small that QGIS considers this to be 0. So here, if we keep on going down, we have e to the minus 9. This disappears. Now we have a few millimeter errors. And if we start looking, here we have a jump from 11 centimeters to 59 centimeters. So what this jump tells me is that probably the people that were creating the networks had a pretty good idea, and they could basically see most of the errors that are under 50 centimeters. The errors that are over 50 centimeters are probably possibly don't need to be fixed. So what we are going to do is we're going to decide to fix all of the disconnected nodes that are under 11 centimeters. And this is done by using the third module. So this is very important to start looking at the distance analysis, because this is what is going to tell you where you need to start correcting. So we are going to choose a number between 11 and 57 centimeters. So we're going to go with 25 centimeters. Okay, now if you want to run Model 3, you need to select the valid geometries, the ones that were corrected in Model 2. It's also important to use the all disconnected node file, which is the import for Model 3. This was created by Model 2. This is the maximum snapping radius. So this is basically based on our observations of the nearest neighbor distance analysis point file. Now, the other variables can be kept as is. Now, the important thing, though, is to not change the variables from one model to the other, particularly the N file, the N field right here. If you start changing this, you are going to have some unreliable results. Once you run this model, you will basically end up with two files. The first file will basically give us an idea of everything that has been fixed and changed. So if we look here, all of these lines have now been snapped and broken up so that all of these have different intersections. This is the only fix that is automatically done by this algorithm. Um, the corrected network is then given here. And this corrected network will need to be rechecked for potential errors by running it again in the model 2. And then that will give us a second run. And in the second run, we will be able to see what has improved or not. Okay, so now we've taken the output from the model 3 and we've rechecked it using model 2. So this is the earlier results that we had. And if we look at the potential problems for the disconnected endnodes, this was from the first run. And now from the second run, we can see that there is a major improvement. Now, there are a few of these that are still around. Now, this is not technically a problem because this end node should not be connected to anything else. But if this is a river network, we would basically need to flip this line to have it go in the other direction. If we look here, so these are all end nodes, and in the middle, this again is an end node. So in the middle of the network, there does not appear to be any end nodes that are not connected. So we can see that there's a major improvement. Okay, now let's see what has not been fixed by the algorithm. The first thing that has not been fixed is the vectorization direction changes. So this is something that will need to be fixed by the user manually. You need to recheck to make sure that the disconnected first and end nodes are all looking good. So here, we can see that things are looking bright. There is, however, an example right here that seems to indicate that we have an end node or a first node that is not connected to the line. The reason for that is that we have an overlapping line here. So in orange, we can see that there are two objects that have overlapping line and one was not connected to the network. And so these overlapping lines will need to be corrected manually. So we have the closed line here. So if this basically was a lake, this would be a problem. A lake should be represented by the center line and not by the side of the or the shore, the lake shore. So this would need to be fixed manually. The overlapping lines, as we can see here. So here we have an object overlapping itself. So object 136 starts here, goes there, resnaps here, and then continues. So 139 is a object that is overlapping with itself. Here we have an example of two objects which are overlapping. We have the object here, which is 142, which goes like this. And then we have an object here, which is 141, that goes like this. So this would need to be manually fixed. So lines that are not touching, so the first or last node, we can see that there are a number of these that are not connected. So these are represented by green. So these would need to be connected to the network. it could be able to connect these using a bigger threshold, but then a lot of the other lines that are much closer would also be connected. So this is a good idea not to do it automatically, but to do it manually. So we have another example here of a line that is not connected to the network by either the first node or end node. As we can see down here, we have the same situation where we have a little overlapping segment that is not connected, and that is mainly because the other line passes under this one. So it's not connected. This would need to be connected here in order for this error not to be flagged. Then we have another potential problem which has not been fixed. It is basically the crossing lines. So here we have two lines that are probably crossing here that would need to be probably looked at. And then we have this intersection here. So this is only a problem if this is not an overpass like on a highway. So if you needed to snap this, to break and snap this, it would probably be easier to do it manually. And this has also given us this little segment here, which was not snapped, which it was not flagged before, because basically we have this line overlapping that line right at this intersection. However, this error was not flagged because this object is connected to this object right here, and object 822 is connected to the object there, which is right here. So technically, these are perfectly snapped, but this does flag an intersection that is, in this case, most likely an error that would need to be corrected manually. Then we have the parallel edges. So the two objects that would possibly need to be corrected, especially if you're using a simple graph, it would be this one would need, and this one. They're basically connected to the same first and second edge. So if you were using a simple graph, one of these lines would disappear unless one possible way out of this would be to simply split one of these lines into two to recalculate the proper lengths. And then this would be basically three lines. One that is first node here, last node there, and then we would have a small line here, and then a bigger line there, and we would no longer have parallel edges. Finally, the last error we are going to be looking at is the overcomplicated lines. So if we look at the lines that could be merged, we have a situation here where we have 1, 2, and 3 lines that could very well be merged as a single line. We have the same situation here in this area also. And this is a problem only if your graph is very, very large, or if you have many hundreds of shortest path analysis to make. If speed is not a problem, then you can leave all of these overly complicated lines alone. This can be merged in QGIS. Just keep in mind that you are also going to be merging the databases. So this can complicate things. The last thing that we are going to look is the final graph. As we can see, the network has been definitely fixed in this area here. So now we have a graph that is well connected. And before we ran the model, the situation was quite different, where we had multiple disconnected line ends. So this pretty well sums up what the the three models can do for you. If you have any questions, you can go on the website and follow the link to my email, and you can send me an email directly. You can also ask a question on the QGIS user group, and I will be happy to answer them there. Thank you very much, and good luck with your network.